All right, so in our last lesson, we talked about solving systems of equations by graphing. However, we did look at an example that kind of showed the problem of graphing is that if we have something that doesn't give us nice, pretty numbers, graphing is pretty hard to do by hand. And even if we use a graphing utility like we did in one of our examples, we still end up with stuff that we have to round. And so that's where it comes into handy to have other methods. And our main two that we're going to look at are substitution and elimination. So our first method that we're going to look at is our substitution method. So our steps for substitution method. Our first step is going to be to solve for one of the variables. Now, depending on the way that the equation is written, one of our variables might already be solved for, which is super handy, or one of our variables might be easier to solve for than the other. So we always want to take that into account when choosing which one to solve for. You can solve for either one, but in some instances, one will be easier than the other to solve for. Then our next step is to substitute, which makes sense because it's called the substitution method. So it makes sense that we would substitute something. So we're going to substitute the expression from above, meaning the expression that we got for that first step, into the other equation. So note that in our first step, we're going to solve for one variable in one of our equations. That means that we still have another equation left. And that's important that we then use the other equation in order to substitute. And that's important because if we used the same equation, everything would just end up disappearing. And we would go, I don't know what to do now. So just remember that we have to substitute it into the other equation. So then we solve for the remaining variable. And then we're going to back substitute. So we're going to take whatever we get as our solution for our first variable, plug that back into one of our equations to be able to solve for the other. So let's look at an example of using this. So it says use the substitution method to solve the following. So we have 5x minus 3y equals 23. And then we have 2x plus y equals 7. So I'm looking at my two equations, and we need to decide which variable do I want to solve for, and then which equation do we want to solve for it in. So looking at those, I notice straight away that in my second equation, I have a coefficient of 1 in front of my y. And that's important because anytime that I have a coefficient of 1, it's going to be much easier to solve for because we're not going to end up with fractions. And if you are like most of the students that I've had in the past, I know that y'all don't like dealing with fractions. Sometimes they're unavoidable if all of our variables have coefficients, but if we can get away without having to use them, that's usually beneficial. So I'm going to go ahead and solve for y in that second equation. So I would subtract 2x from both sides, and I end up with y equals negative 2x plus 7. So recall that we used equation 2 in order to solve for y. So that means that my next step is to substitute what we got for y back into our other equation, which means that I need to use the first equation. I have y equals an expression. So in my first equation, I'm going to substitute that y value for what I got from my second. And then we're just going to solve. It's a two-step or multi-step equation like we've seen since Algebra 1. So recall that we need to distribute that 3 to both of my numbers. It is a negative 3. So negative 3 times negative 2 gives me a positive 6x. And then negative 3 times 7 gives me a negative 21. Combining my like terms, I get 11x minus 21 equals 23. I add 21 to the other side, divide by 11, and we should get x equals 4. So then our next step is going to be to take what we got here, x equals 4, and back substitute. And we could plug it into any of our equations. However, notice that in my second equation, I already have an equation that is equal to this one. So I'm allowed to use it, and y is already solved for, so I won't have to solve for anything. So if we use that second equation, we would get y equals negative 2 times 4 plus 7. I'm just plugging in my value that I got for x into that equation. So then if we simplify, negative 2 times 4 is negative 8, plus 7 gives us a negative 1. Now, if we recall from our last lesson, we said that our solutions for systems are points of intersection, and that's going to be true even when we're not graphing them. So here I used a different method besides graphing, but I still want to write my final answer as a point. So notice that my x value, which is going to go first, is 4, and my y value is negative 1. So that would be my solution to my first question. Now, on my second question, I have x minus 7y equals 11, and 5x plus 4 equals negative 23. Again, I want to look and see, is there one variable or one equation that's going to be easier to solve for than the other? And in this case, it's going to be my x, and it's in my first equation. Again, because that leading coefficient is 1, it makes our lives a whole lot easier to solve for x. So we get x equals positive 7y plus 11 by adding that 7y to both sides. So I solved for one of my variables. Now I need to plug that expression into the other equation. So this time we use the first equation in order to solve for x. So that means that I need to plug it into the second equation in order to solve for y. So plugging it in, again, we have a multi-step equation, which is okay. So distributing our 5, we get 35y plus 55 plus 40y. That negative 23 hasn't changed. So we get 39y plus 55 equals negative 23. So 39y equals negative 78 by subtracting 55 to both sides. So we get that y equals negative 2. Again, we have to back substitute in order to find out what our x is. Again, we could do it into any of our equations, but let's go ahead and use the one where x is already solved for. So we get x equals 7 times negative 2 plus 11. So 7 times negative 2 gives us a negative 14 plus 11 gives us a negative 3. Again, we want to write that answer as a point, but be careful because remember that our points go in alphabetical order. So just because I found my y value first doesn't mean that I write my y value first. I still need to write that x value first and then my y value. So negative 3, negative 2 would be my solution. All right, so next up we have our elimination method. So we're going to multiply one or more of our equations by a number to result in opposite coefficients for one variable. That sounds like a mouthful, but we'll look at what that actually means here in our next example. But let's still go through the steps. So next, once we do that, we want to add the equations. Then we're going to solve for the remaining variable. And again, back substitute. So like I said, let's look at an example of what this actually means practically. So we have 5x plus 3y equals negative 19 and 8x plus 3y equals negative 25. And my directions say to use the elimination method to solve the following. So I want to use the elimination method. So again, just like with substitution, one of our variables might be easier to use than the other. And most of the time, that's going to be dependent upon what our coefficients are. So I notice right away that my y's both have a coefficient of 3. And so what we want to do, like our direction said, is to multiply by something so they have the opposite coefficient, which is nice because if I multiply one of those by a negative 1, I end up with opposite coefficients. So our resulting new system would be 5x plus 3y equals negative 19. And then our second would be negative 8x minus 3y equals a positive 25. Now, you might be saying, well, couldn't I have just subtracted instead of multiplying by that negative? And the answer is yes, you can. The only thing to be aware of or to consider is that when you subtract your two equations instead of adding, it's really common for students to get over to our whole numbers and forget that you're subtracting, and then they'll go ahead and add instead of subtract. So just be careful. If you want to skip the step of multiplying by negative and go ahead and just subtract, that's fine, but just be careful with those algebra steps. So in my case, I am going to add my two equations. So we have 5x plus a negative 8x, which is going to give us a negative 3x. And the whole reason that we do all of these steps is because notice I have 3y plus a negative 3y, which gives us 0y. Or in other words, our y has been eliminated, which is the reasoning behind why it's called that. And then I have negative 19 plus 25, which is going to give me a positive 6. So then rewriting that equation, I have negative 3x equals 6. Now we want to solve for that remaining variable, which in this case is x. And so we get that x equals negative 2. But we're not quite done. Remember that we do still need to back substitute in order to figure out what our y value is going to be. Now in this case, because we didn't solve either equation for a variable, it's not really going to matter which one we plug into. So I'm going to go ahead and plug into my first equation, but you would get the same thing by plugging into your second equation. So we get 5 times negative 2 plus 3y equals a negative 19. So simplifying, we get negative 10 plus 3y equals negative 19. Adding a 10 over, we get 3y equals negative 9. Dividing by 3, we get that y equals negative 3. Do be careful on adding this negative 10, because a lot of us want to write negative 19 there. Sorry, negative 29 there instead. So just be careful with those algebra steps. So again, remember, I want to write my answer as an ordered pair. So my x value comes first, my y value comes second. So negative 2, negative 3 is going to be my answer. All right, so next up, we have 5x plus 3y equals 52. 15x plus 9y equals 54. So if we notice, I'm going to go ahead and use our x value to eliminate. And the way that we do that, and the way that I notice it is, look, I have a 5 and I have a 15. That's nice because 5 can be multiplied by 3 in order to get to 15. So I'm going to go ahead and multiply that first equation by a negative 3 because I want them to be opposite signs. So my first equation is going to turn into negative 15x minus 9y equals negative 156. Rewriting my second equation just as it stands. And some of you might already be ahead of the game and say, oh, those are both opposites. What's going to happen? Well, let's find out. So again, we want to add those two equations. So negative 15x plus 15x gives us 0x. Likewise, I have a negative 9y plus 9y also gives us 0y. And then I have negative 156 plus 54 is going to give us a negative 102. So simplifying my left side, I just end up with 0 equals negative 102. Now, hopefully we're all good enough math students to know that 0 does not equal negative 102. So I maybe want to go back and double check my steps, make sure I didn't mess up anywhere. In this case, we didn't. We just ended up with a false statement. And what that means is that no matter what I plug into the first equation or the second equation, there's no way for me to end up with them intersecting. And so that tells us that we have no solution, which is okay. Sometimes a system has no solution. And hopefully we remember from our graphing that that means that our two graphs are going to be parallel.